Okay, so welcome everybody to this edition of the ICTS virtual string seminars. Today we have Noppadol Mekareeya with us. He's at the INFN in Milan, and he's going to talk to us about supersymmetry enhancement in 3D S-fold theories. So, to you, Noppadol.
Thank you very much for the invitation, and it's a great pleasure to give a seminar well, even it's a virtual, but thank you very much for the invitation. Would love to be one day in Rio there. Yes, so my talk will be about supersymmetry enhancement in a collection of three-dimensional field theories, which is, I would say, not so well known, this class of theory. It's arise in quite a simple way and provide a collection of model, which is superconformal in the infrared that have interesting behavior, okay? So this is based on a series of paper with my student, Ivan Garozzo, here in Bicocca, Gabriele Lomonaco, which is now in Saclay, Matteo Sacchi, who is also student in Bicocca, Emanuele Berato, which is also my student in Bicocca, and this is a recent paper, okay? So the main goal is to introduce a new class of 3D superconformal field theories. And basically, this is has something to do with the duality walls in this is type of S duality or SL2Z duality walls, if you like, in the S4D n equal to 4 super Yang-Mills theory. The description of this theory, as I will show you, has at least n equal to 3 supersymmetry. But later we will show you that supersymmetry and flavor symmetry can get enhanced in the infrared. And okay, this is a usual phenomenon in the renormalization group flow. And there are many interesting duality. And this is a generalization of a 3D mirror symmetry due to interrogators and Seiberg. Okay. So,
the n equal to 3 is 3D n equal to 3?
Yes, exactly. So we are in 3 dimension. Okay. Yes, this is 3D superconformal field theory. Yes, so this, I'm sorry, yeah, I should have put 3D here, not to confuse with this 4D n equal. So it's associated with duality wall of 4D n equal to 4 super Yang-Mills, and the theory has at least 3D n equal to 3 supersymmetry, okay?
So just to make sure that, so this is SO3 is our symmetry group?
Exactly.
Okay.
At least SO3, yeah.
Okay, thanks.
Thank you. So let me give a brief review on 3D n equal to 4 gauge theories. So this theory in general has a, has SO4R symmetry, which you can call it SU2, V and SU2H. So one way to view this 3D n equal to 4 gauge theory is to use a type 2B brane setup, which is sufficient for our purpose for the moment. So you can look at the system of D3 and S5, D5 spanning this direction, and you can focus on the gauge theory on the 0, 1, 2 direction on the volume of the D3 brane. And as you can see on the transverse direction, there's SO3 times SO3. This is identified as R symmetry, okay? The position of D3 in the direction of, depends on how you call it, 3, 4, 5 and 7, 8, 9 direction correspond to the vacuum expectation values of the real scalar in the vector multiplet and the hypermultiplet. Okay, so an example would be U2 gauge theory with 4 flavor in the fundamental hypermultiplets. This is the notation that I will use throughout the talk. So this is quiver basically. So you have 2D3 stretch between 2NS5 and 4D5 brane. Okay, you can also move it out with the brane creation. This is well known from Hanani-Witten. Okay, so the vacuum space of this theory, there are 2 main branches. One is Higgs branch and one is Coulomb branch. The Higgs branch parameterizes vacuum expectation values of scalar in the hypermultiplet. So the way to see this is to take this picture, and then you split the D3 between D5 brane. So after splitting, you get this picture. And basically, you can see that this segment can move along the D5 direction. And this is the vacuum expectation value of the scalar of the hypermultiplet. And yeah, if you count it, there are 1, 2, 3, 4 of them. And these are 4 real scalar that parameterize the position of the D3 along the NS5 brane, okay? Along the D5 brane, I'm sorry. This is the D5. So 4 real scalar, where did they come from? 3 real scalar come from 7, 8, 9 direction. There is another scalar, which is due to this gauge field, which we call B, and this bosonic part of the hypermultiplet. So there are 4 of them. And equal to 4, supersymmetry requires that the Higgs branch is hyperkähler. And this branch is well known that does not receive quantum correction, okay? There is another branch, which is called the Coulomb branch, which you separate D3 in opposite way. Now you separate it along generically along NS5. Again, there are 4 real scalar for each D3, 3 real scalar associated with now another direction, 3, 4, 5, and another scalar due to each U1 gauge field. In this case, because we have gauge group U2, you can take this to be UO photon inside the U1 inside this U2, okay? The Coulomb branch is hyperkähler, again, due to n equal to 4 supersymmetry. And the dimension of Coulomb branch is just the number of D3 brane that connecting NS5 brane, which is the rank of the gauge group, which is 2 in this example. In general, yeah, as I said, the total rank of the gauge group is basically the dimension, quaternionic dimension of the Coulomb branch. We count in quaternionic unit because everything comes in unit of 4 real, okay? And the Coulomb branch is isomorphic to, classically, is isomorphic to R3 times S1. R3 because these are 3 directions. S1 coming from the compact scalar due to the U1 gauge field. Square because we have 2 of them, okay? Yeah. So this classical picture. But it's well known that the Coulomb branch receives quantum corrections. The reason is because you can take gauge field to become a background field inside this SU2R symmetry. And if you compute the metric at weak coupling, you see that the gauge field can enter into the gauge coupling can enter into the metric, okay? A suitable description for the quantum Coulomb branch is basically to use monopole operator with a combination of the scalar of the vector multiplet. So I will describe this soon, but before describing the monopole operator, I would like to mention another global symmetry. This is called the topological symmetry associated with this theory. So if you have a gauge symmetry, which has a U1 factor, in this example, we take U2 gauge group, right? So there is a U1 factor inside. So this gives rise to a global symmetry, which is known as topological symmetry, commonly denoted as U1J, okay? So if you take this U1 factor, you dualize, you get the J here, and you see that J is conserved. And this is the current associated with the topological symmetry U1J. Now, because of this, you see that each U1 factor gives rise to U1J, but the U1J can enhance further in the infrared. And this is quite a well-known phenomenon in 3D theory. Take, for example, U2 gauge theory with 4 flavors. U1 topological gets enhanced in the infrared into SU2. How do you see this? Okay, so this is quite interesting, and we can study this in the language of the superconformal multiplet of 3D n equal to 4 SCFT. So to understand this, one need to study Coulomb branch operator that carry R charge 1. Why R charge 1? Because these are superpartner of the topological currents for 3D n equal to 4. Okay, so this is due to 3D n equal to 4. 3D equal to 4 superconformal algebra, basically, that enough to look at operator at R charge 1, and these are superpartner of the topological current, and you can detect the enhancement. This is enhancement of a topological symmetry. Okay, so I talked about monopole operators as a suitable variable to describe Coulomb branch, right? So how do they arise? So they arise from 3 real scalar in the vector multiplet plus a dual photon. So this become a complex scalar. So you take a combination of 3 real scalar to a complex scalar plus a monopole operator. So monopole operator coming from the UV perspective is come from the combination of dual photon with one of the scalar, basically. So, and you specify monopole operator by magnetic flux. For example, for U2 gauge group, the magnetic flux is labeled by a 2 integer. Okay, there is the Y group action that acting, so you can make M1 greater than or equal to M2, for example. And the monopole operator carry topological charge M1 plus M2. Okay, so for U2 gauge theory 4 flavor, monopole operator that carry R charge 1 are the one that carry a flux 1, 0 and minus 1, 0. And if you look at the theory, there are 3 operators with R charge 1, namely V1, 0, V minus 1, 0, and the trace phi, which is the scalar, basically. And they carry topological charges plus 1 here because it's monopole. You can use this. And this guy carries 0 and this minus 1. So there are 3 of them, and they carry weights plus 1, 0, and minus charges plus 1, 0, and minus 1. These are highest weight of SU2 if you see that. And these are superpartners, indeed the superpartners of the enhanced SU2 current. Okay. So we conclude that there is an enhancement of the topological symmetry in the infrared. So U1J, which visible in the description, enhanced to SU2 in the infrared. So this is quite well known, the behavior of the monopole operator, that it can make symmetry enhanced in the infrared. Okay. So this a review of 3D n equal to 4. The next part, another well-known, is that mirror symmetry.
Sorry, can I just, so can you just go back to the previous slide? So this U1J, the charge is carried by vertices, right? Vertices in the...
Yes, so, okay, yeah. Excellent. So these are monopole. When you talk about monopole, these are at the CFT point. This object, you can also look at it you can track it out actually on a various branch of the moduli space. Yes, suppose that you go on Higgs branch, you can turn on Fourier-Illoupoulos parameter, then this has size. This become vortex, as you said.
Yeah. So is there some way of looking at why this enhancement comes about from the part of the vertices? Is it like they have some mutual phase or something when they go around each other? Or
yes, so basically this charge is basically the phase, if you want. In the UV description, when you form this monopole operator, you exponentiate the real scalar with the dual photon. Mm-hmm. And you can look at topological symmetry as some kind of phase, yes.
Mm-hmm. Okay, and this enhancement can be seen also by approaching it from the Higgs branch?
This enhancement it's best doing it at the CFT point because, okay, excellent. So vortex, as you mentioned, is more like an object that you have to go on the other branch, right? Mm. But the CFT lives on the origin of the moduli space where Higgs branch intersect with the Coulomb branch.
Right.
So when you go to the origin, this object vortex becomes sizeless, basically. That's why they call it monopole operator. They don't have size anymore. So at the CFT point, this is where you can use superconformal algebra to relate these objects to the current, basically. Otherwise, you cannot.
Mm-hmm. So this SU2, this enhanced
superconformal point.
Yeah. Okay. Another way to maybe I can rephrase the question: is this SU2 broken if you move out of this origin of the Higgs branch? Or?
Yeah, exactly. At the generic point, this is so basically when you so basically this so when you move out from so let me see. So when you these are regarded as Coulomb branch operator. So when you move along moduli space, this symmetry can be broken.
Okay, thanks.
Okay. So another interesting feature of this 3D n equal to 4 theory is a mirror symmetry. So this is also another infrared phenomenon of the 3D n equal to 4, that many 3D n equal to 4 gauge theory flows to non-trivial fixed point. There could be dual description at the fixed point, meaning that there could be many Lagrangian that describe the same fixed point. Okay. And suppose that you have two descriptions, let's call A and B. Mirror symmetry regardless theory A and theory B by exchanging Higgs and Coulomb branches of the two theory. Okay. So Higgs of the theory A become Coulomb of the theory B and vice versa. And the dual description can be obtained from the type IIB brane construction by considering SL2Z action, which is specifically S. Okay, so this action, you can see that if you take a basis of NS5 to be 1, 0 and D5 to be 0, 1, this S action, you multiply S with the 1, 0, you get 0, 1, and D5, you multiply S by this and you get minus 1, 0. So upon the S action, you can see that NS5 turn into D5 and D5, you multiply D5 in this basis, it has minus 1, 0. If you also equipped it with a rotation that rotates a certain direction of the space-time, you exchange NS5 and D5, and this is correspond to mirror symmetry, the combined operation RS. So as an example, you can perform RS operation on this brane system that turn D5 into NS5 and write down theory that you can read off from brane. So this is U2 gauge theory with 4 flavor that I described on a previous slide. And this is the dual description, which describe the same fixed point, except that the Higgs branch of A become Coulomb branch of B. Indeed, if you count the dimension, we learned that Higgs branch of A has dimension 4, Coulomb branch has, because gauge group has rank 2, is dimension 2. And if you apply the same method, you see that the dimensions get exchanged. So on this, you see that this is quite interesting phenomenon, that the enhanced SU2 topological symmetry of the theory A is manifest as the flavor symmetry of theory B. Okay, so U1J that enhanced to SU2J in the description A become manifest here. Similarly, theory B has U1 cube topological symmetry because you have 3 unitary gauge group, get enhanced to SU4, which is manifest in the flavor symmetry of theory A. Okay, now let me answer the question of Tom. So you can see that here is manifest here, right? So as you know very well that if you go along the Higgs branch, flavor symmetry is broken, right? Because you give a web to the hypermultiplet. Here, since the Higgs branch of this description become Coulomb branch of this description, you can see that if you go along the Coulomb branch, topological symmetry is generically broken. So this is one way to see it. It's a mirror description of these two. Okay. So right. And this is S action of SL2C.
I have a question.
Yes, please.
Yeah, so actually that's a good slide. So is it always true that if you have a non-abelian flavor symmetry for a 3D n equal to 4 theory, then its mirror is going to have this enhancement of the topological symmetry?
No, not at all. Not at all. Take U2 with 5 flavor, there's no enhancement. This enhancement is due to the fact that this monopole operator has R charge 1. And this is very specific to 4 flavor with U2 gauge group. Suppose you take 5 flavor, then this no longer has R charge 1. So it has R charge 5, I think 5/2. No, wait. Sorry, it has some R charge, which is higher. Then the only operator that has R charge 1 is trace phi. And you conclude that superpartner, there's only one superpartner of the current. So U1J remain U1J.
Okay, thanks.
So yes, so this is why I highlight these two in blue, is because it's in this case, because of 4 flavor, it has a precisely R charge 1, and there are 3 guys that transform under SU2. Okay.
Yeah, thanks.
Okay. So now the T action. So yes, so this I described the S action, which is identified as mirror symmetry. There is another action of a generator of SL2Z, if you like. This is the T action, which an S5 brane transform into 115 brane, and D5 brane is invariant under this T action. And so basically, if you have 1K5 brane along with D5 and an S5, it gives rise to Chern-Simons level. The prescription to do this is that suppose that you have to have 1K5 brane, let's call 1K1, 1K2, and an S5, which in the basis we call 1, 0. You can subtract the pairwise difference, K1 minus 0, K2 minus 0, K2 minus K1, and 0 minus K2, and read off Chern-Simons of the gauge theory just from this system. So you can generate also some duality. For example, you can consider T transpose, which is minus TST, which turn D5 into a 1, and leave an S5 invariant. So you have this description. You transform T transpose, you change D5 into 1, and get this description, and you can read off. So you can see that 1, 3, when U1 with 3 flavor become Chern-Simons matter theory. What is interesting is that even this has Chern-Simons level. Usually it's believed that the theory in the description has n equal to 3 supersymmetry in 3 dimensions. But since this is dual to n equal to 4 supersymmetry in 3D, so these two should have n equal to 4 also, okay, by duality. So we will look at this class of theory later in the talk, and we will describe how to detect this enhancement. So, okay, so now all the introduction that I said is that to introduce this type of theory. This is called TSUN. So TSUN is a 3D n equal to 4 theory that has a quiver description. It flows through the infrared fixed point again, that has interesting behavior. First of all, this theory is self-mirror, meaning that if you apply mirror symmetry, you have the same quiver back. Okay, so how do we see that? We draw the brane picture and we see that upon swapping NS5 and D5, you get the same picture. So this is invariant under S duality. So yes, it is a self-mirror theory. The Higgs branch and Coulomb branch are the same, of course, because mirror symmetry exchange Higgs and Coulomb branch, so they must be the same if they're self-mirror. And indeed, it say that it's isomorphic for the nilpotent cone of SUN. Okay, this is the description of nilpotent cone. Not so important for us. You can check that Higgs branch dimension and Coulomb branch dimension are the same. Now, okay. Now the Higgs branch symmetry algebra SUN is manifest as flavor symmetry. Again, let me remind you that the Coulomb branch you can only see from the description as U1 to the n-1 because there are n-1 unitary gauge group. But since the theory is self-mirror, you can expect that they have to enhance to the IR. And indeed, you can check the, again, monopole operator that there are n square minus 1 in the infrared, okay? Now you can see that one of the global symmetry is in fact UN mod U1 or SUN mod ZN. For the reason that if you look at this flavor symmetry, there's a gauge rotation in this flavor symmetry. You can absorb it into the, there's a U1 action on this flavor symmetry that you can absorb into a gauge rotation, okay? So basically, so you take this to be UN, but you have to mod U1 because this is an act on anything. So, or you can take it to be SUN and you can say that the center of SUN doesn't act on this thing. So the global symmetry is in fact SUN mod ZN, or one of the factor. And there's no, meaning that if you weakly gauge this node, okay, you don't have topological symmetry, okay. So this is also consistent with the fact that in TSUN as an SCFT has global symmetry, SUN time SUN check. Check mean the Langlands duo of SUN, which is SUN mod ZN. Okay, so these are the global symmetry of the theory. And one can couple TSUN to the SUN valued and SUN mod ZN value external gauge field. So this is property of a TSUN due to Gayoto-Witten. I just review. Another important point is that you can associate this theory with a domain wall in the 4D n equal to 4 super Young mills. Let me demonstrate how. Again, this is due to Gayoto-Witten. So this is the description of the TSUN. TSUN is a name for the infrared fixed point of this theory. So the claim is that this theory arises from a domain wall of some super Young mills theory. So basically, we can consider something called a Janus configuration, which is interpolate between weakly coupled and a strongly coupled n equal to 4 super Young mills. Okay. On the left-hand side, okay, this the degree of freedom decouple. So you are left with the Dirichlet boundary condition on the right. So to describe this Dirichlet boundary condition, you can look at half space theory as a D3 brane. The super Young mills is on the D3 brane, ending on D5, right? So when the brane ends, you impose the Dirichlet boundary condition on the gauge field on the D3 brane. Okay, now, so, okay, this is the same sentence from the last slide that the right-hand side here is D3 ending on D5. However, on the right-hand side, as you observe, this is a strong coupling regime. You cannot do much in reading a description. So the trick is to do S-duality. So apply S-duality to the theory on the half space on the right. So the dual description become D3 brane ending on NS5 brane. So you change D5 to NS5 upon S-duality. Now the 4D field now weakly coupled. So, okay, all of that become weakly coupled. So you can decouple by placing the other end of D3 brane by additional D5 brane. So remember, on the right-hand side, once you S-dual, you have D3 ending on NS5, like this. And on the left, you can end it on D5 because this is a decoupled system. And then you have the description as claim, as a quiver that look like 1, 2, 3 up to n. Okay, so this is the argument of Gayoto-Witten basically to associate the TSUN with the domain wall of the 4D n equal to 4 super Yang-Mills. And observe that because of S-duality, if you take one side to be SUN, upon doing so the strongly coupled will be SUN mod Cn. Okay, so it has to be Langlands dual to each other. Now there is another close cousin which will play an important role in our theory. It's called TUN. So what is TUN? So basically you introduce something called TU1. TU1 is basically an almost empty theory. It's not quite empty because although it has no matter or no vector multiplet, no hypermultiplet, nothing. But it has a prescription for coupling external abelian vector field. So when you have TU1, you declare that if you have two U1 gauge field B and C, there is a prescription to couple them together by the SUSY completion of a C wedge DB. So this is basically mixed Chern-Simons or BF coupling, if you like. So this is just a basically theory with this type of coupling, basically. This is a mixed Chern-Simons term between two U1. Okay. Now, what is interesting is that you can construct TUN theory by just consider a product of TSUN times TU1. So now TSUN is as you see before, and now TUN declare that when you have TU1, you couple them together by this type of coupling. So you can couple TUN to the UN value and the UN check value, but UN check is just UN, external gauge field, okay? So, of course, there is a Chern-Simons coupling between the U1 gauge field that gauge the center of UN and of the two UN, okay? So this is an interesting theory. Now, so this will play a very important role in the construction of our theory. Basically, this is well known from a Gayoto-Witten. This part is review part from the result in 2008. Okay. Now, why this become more interesting? Because we have seen a concept of some duality wall in the earlier slide, but you can even make it use it in a more stronger way in certain sense. In the following way, that you remember the S matrix and T matrix I introduced earlier. If you act on the PQ, it changes into minus QP, and the T, you get P plus Q, okay? So what does it mean here? So the one interpretation is that if you introduce the PQ brane, you can trade it with this system. So meaning that you can trade PQ with Q minus QP system in between S and S inverse wall. So basically the duality wall just introduce a boundary of the region where the local SL2C action is performed, right? So basically you introduce this as a new object in the brane system. And then you look at the action.
Noppadol, I have a question.
Yeah.
Yeah, sorry.
Please.
Actually, if you could go to the previous slide.
Yeah.
So the TUN theory, what are its Higgs and Coulomb branches? Are they again the nilpotent cone?
Excellent question. Suppose that you don't turn on any background flavor symmetry. It will be the same as TSUN. The local operator is the same as TSUN.
Okay.
However, you see, when you have, suppose that you turn on background symmetry for the flavor symmetry, say Higgs and Coulomb symmetry, there is a mixed Chern-Simons. But this mixed Chern-Simons was acting in a flavor symmetry, not a gauge symmetry. Once you suppose that you gauge this thing, you can detect it. But if you don't gauge it, you don't detect it.
I see. Okay.
Okay. So I claim that there is a mixed Chern-Simon between two Higgs and Coulomb symmetry, basically, of this theory, but it's on the global symmetry side. So it's like a background mixed Chern-Simons, if you want. Is that clear?
Okay. Okay.
Sorry, Noppadol, sorry, I just realized. So how do we say that there is actually a mixed Chern-Simons term? Is this some statement about some kind of a discrete anomaly in some Z2? Is there a way of saying it that way, that like let's say if I take B going to minus B and C goes to minus C.
Yes.
Now, if this coupling was not there, you would say that, you know, like they are independently symmetries of the theory. Isn't that
so? If there is no mixed Chern-Simons, then you are in TSUN, right?
Yes.
So you are in TSUN, then on one side you have SUN mod ZN, and the other side you have SUN symmetry,
Yeah.
flavor symmetry.
Yeah. What I was thinking of, just that, you know, like I want to construct a theory which is like TUN, but without this Chern-Simons term.
TUN without Chern-Simons, but I don't know how to couple external gauge field in the UN way. So you said that you might want to do, and you have anomaly. Is that what you are suggesting?
Yeah. Is that the statement? I mean, how do
yes, there's there is some kind of, well, this statement is not very well known. I think this is it would be nice to clarify this option, whether. Okay, excellent question. Suppose that, so let me formulate your question maybe. That you suppose that you gauge this symmetry together, which I would do in the second part of my talk. How much you can do this without anomaly, right? Without gauge anomaly.
And do I have to add the Chern-Simons term to be able to do that somehow?
Yes, this is important.
That somehow you should cancel the anomaly, so to speak. Some parity anomaly or something.
With this mixed one, I cannot answer this question in a sharp way. Suppose that you, okay, I can tell you that there's no problem if you turn off this Chern-Simons. I mean actually there is, if you don't couple extra matter to it. I will probably can comment later at towards the second part of my talk, because I will gauge these two symmetry together.
Okay, thanks.
And if you don't do it carefully, there's something wrong with the theory. Yeah, that's right. So yes, so what I'm saying is that you can view S duality wall as a new object in the theory, and indeed you can isolate this object. Okay, so what is the claim of this is mainly due to Gaioto-Witten and Gulota, Herzog, and Pufu, is that if you manage to isolate the action of each wall, which you can do on the level of S3 partition function on this. So basically you write S3 partition function of the phi brane, PQ phi brane, okay? And you try to isolate the action of this wall. What you will find is that it introduced like a piece. So suppose you have ND3 and you isolate the action of the S wall. What you can see is that there is a 2UN symmetry coupled by TUN. Now you can see that ND3 brane introduced 4D n equal to 4 super Yang mu on each side, right? You take that and associate with the 3D theory, where the 3D theory is just TUN coupled to external vector multiplet, which is UN and UN. So, okay, this is the picture. And the T wall was basically to shift Chern-Simons by 1 in 3 dimensions. So these S and T walls were studied using matrix model on the S3 partition function of the corresponding 3D theory. Okay. So now we can construct the theory that we would like to. So this is the main part of the talk. So this is called the 3D S-fold SCFT. So why is it called S-fold? Because we basically fold the theory together using the SL2C twist, basically, if you want. Okay, so what we do, we insert SL2Z duality walls into a type IIB brane system. And this is usually a circular system. So the theory contains TUN link with a possibility of Chern-Simons level. So you can have a look at this example. So suppose I take a ND3 on a circle. So my low energy limit, I get some 3D theory, okay? And I put the wall on this. Suppose that I put J1, JK1, JK2, and JK3 in the picture, where JK is defined as minus T to the K. And this is an element in the SL2Z. This is called the JK4. Why is it called JK4? Because when I introduce this thing, I introduce local JK action at the wall. So basically, you can see that according to these slides, you introduce the object, which is basically coming from the contribution of this wall. In this case, if you introduce 3 walls like this, you will have 3 UN gauge group. You read it as almost like in a brane picture, in a Hanani-Witten setup. So there are 3 UN, but now you have to take into account of this JK action. Since each wall introduced TUN link, each gauge group, instead of bifundamental method, you have TUN theory coupled to each of them. And T to the K also introduced Chern-Simons level K1, K2, K3. So this is one example. And any SL2Z element can be put into this form, basically. So you can just look at the product of the minus ST to the K, basically, up to a conjugation. Okay, so this is the theory that I'm going to study in the rest of the talk. Also, you can add matter to this type of theory. For example, you can add an S5 brane or D5 brane. So for example, if you can add, if you put one wall, this would give rise to UN times UN, right? With the level shipped by K on one side. And you put D5, 2D5 will introduce 2 flavor of the fundamental hypermultiplet to this UN, and NS5 will introduce a bifundamental hypermultiplet. So this is the type of theory. Any question on this construction? So why this is interesting? Sorry, yes.
Just one question. So are the usual orientifolds included in this set of?
This is not orientifold. This is not orientifold. This is okay. It's a fixed wall. It's a fixed. This is a duality interface, if you want, right? So meaning that it's in the following sense that if you move, let me answer your question. Maybe these slides. I don't know. It's clear. You can tell me. So suppose that you have a D5 brane on one side. You move it across the wall, like do it in this picture. This D5 brane experience the JK action and turn into an S5 brane. So it's an interface where you impose the JK action whenever you cross it. Is that clear? It's different from orientifold in the sense that orientifold flip the space-time, right? Introduce Z2 symmetry, but on space-time, right? In this case, it's only introduce the SL2Z action when you cross it.
So a D5 brane going through this wall would in general become some PQ5 brane, is that?
Exactly. Specifically, you can take the JK matrix, as I wrote here, and you multiply by the appropriate basis of the D5, which is what we choose is 0, 1. And then it becomes 1, 0. So we conclude that the D5 turned into an S5.
And vice versa, the NS5s will also turn
exactly, and exactly. You can multiply this matrix and determine what it becomes. So you can see that what is interesting here is that because of TUN, you know that TUN has Higgs and Coulomb And you can couple vector multiplet in UN and UN. So basically you see that you couple UN of one TUN with the other UN of the UN basically. So this is that's why it's quite interesting that you gauge all together now the symmetry that you have in TUN theory. Okay. So now this is an interesting duality, as you can see. Why is it interesting? You can start from one frame. In this frame, you have single UN gauge group with a K Chern-Simons level K because of this K. Okay. You put the ND5 brane, which is give rise to N flavor, and this has TUN. Okay. This is not adjoint matter, but this is you should look at it as a SCFT with UN times UN, and you commonly gauge the UN. This is why it's become commonly gauged, the two symmetry. And you can see that the level, now I give the level K to this, according to this JK action, okay? Once you move NS5 brane across this, it become, sorry, when you move D5 brane across this, it become NS5 brane. And now you can read another brane picture. This is N-1, okay? So it gives rise to N-1 flavor. NS5 brane become a bifundamental hypermultiplet. So you can do this and you can repeat this process until you get bored. And now you have at least 3 duality frames. Of course, you can keep doing more and you generate more and more duality frame. So basically, if n is, this small n is large, you can keep doing it basically, and you generate a duality frame. And you can see that all of these duality frames are generated by one action, which is JK here, minus ST to the K. So this is, I claim that this is a generalization of a 3D mirror symmetry because you use both S and T together to generate a duality frame. Okay, so basically, commonly gauging UN Higgs branch symmetry with the UN Coulomb branch symmetry of a TUN explicitly break R symmetry of the n equal to 4 theory, which is SU2 Higgs and SU2 Coulomb, right? To SU2 diagonal, because you commonly gauge the symmetry. So Higgs symmetry and the vector symmetry got combined into diagonal. So would you say, you would say that because of R symmetry look like an SO3 now, or SU2 diagonal now, the quiver description should have 3D n equal to 3 supersymmetry. However, if you look at the theory, so there are 2 perspectives on this. One perspective is done by Assel and Tomasiello. So what they do is they look at POJ4. POJ4 means that you don't add any matter. You take in the large n limit. The supergravity solution seem to suggest that this SCFT has n equal to 4 supersymmetry. So how?
I have a question.
Yes. Please.
So let's say we do look at theories that have a UV Lagrangian.
Yes.
So is it not true that there is no description in which the 2 global symmetries, the one on the Higgs and one on the are manifest, right? Even if we are lucky and the theory and its mirror both
yes,
have Lagrangian.
So this is, if you like, this is quasi-Lagrangian. This is not a real Lagrangian because you can claim that both Higgs and Coulomb symmetry do not manifest at the same time in the description of TUN. This is, I agree. But I'm not talking about Lagrangian of TUN. I'm talking TUN at a fixed point. So you have 2 UN current, you agree, which you can gauge.
Sure.
It's like,
but
it's like,
I'm trying to understand what it means.
It's like when you do E6 theory of T3 theory class S, you say that, oh, E6 is not manifest in description, or I don't know, take any theory with the global symmetry enhancement, but you can talk about CFT at infrared and couple the CFT to something else, right?
Yeah,
so
sure.
What I'm doing here is the same. I take this CFT, which is TUN, which has 2 UN current, And then I couple together to form this system. So this is per se not a Lagrangian. This is, you can call it quasi-Lagrangian. Some people call this even other name, quivering. Yeah, but so this is not a Lagrangian.
Should I literally think in terms of?
You should literally think TUN as a CFT. So this red line is a CFT.
Okay.
It's like a Kyoto block, basically, if you want, right? Like T3, that you always write it as a triangle with the T3 and then a lot of symmetry, and you gauge it, you do a lot of things with it. It's a similar thing. This is in 3 dimensions, and it has UN times UN. It's in that sense. So what I'm saying is that the POJ for the gravity duo of this is known, and you can match free energy of the quiver theory in a large N limit with the supergravity calculation, and it matches nicely. Now you can ask, okay, what about when you add matter? This is not doesn't have a clear gravity duo anymore. This has a good gravity duo at large N. This, for example, is not clear. And also, what about at finite N? So basically our work, the main goal of this talk basically is to show you how to detect this supersymmetry enhancement at finite N. You can show this at whether there is a matter added or not, okay? And some model even have a further enhancement of supersymmetry to even N equal to 5 supersymmetry. So let me show you. So our main tool is the supersymmetric index. So probably it's well known to many of you that this is a trace of the basically on the S2 times R with this thing. Let me not go into detail because of the lack of time also. And you can use localization to put it in a nice form that receive contribution from the classical piece, vector multiplet, and the hypermultiplet, okay? So if you take TU2 or U1 with 2 flavor, this is how it look like. Although on this slide look like a mess, but okay, it has a fugacity flux, it has a flavor symmetry and the background fluxes, and it has a topological symmetry and background fluxes. To form a TU2, what you could do is that you have to, okay, multiply by the mixed Chern-Simons term. Okay, this is where it gets interesting, and this probably answers some question that you have earlier, that how, in terms of partition function, how do you write TU2 explicitly? So indeed, this is TSU2, and you multiply some factor. This factor, what does it do? It imposes the self-duality of the theory. So you can see that you can swap topological fugacity and fluxes with the flavor fugacity and fluxes, such that you don't have to impose the condition on the SUN, or in this case, SU2, okay? So it's true without this condition. You can just swap it, and this factor came out. And this is the, indeed, if you look at it, it's a mixed Chern-Simons term between the topological and the flavor, okay? Now, for S-fold theory, you just commonly gauge both U2 symmetry in this partition function.
Sorry, Noppadol, so
yes.
How do you see that there is a mixed Chern-Simons term contribution? You can just
okay, excellent.
Or,
so if you look at this, my notation in TSU2, okay, there is a two parts, okay? So F and N, this is flavor, fugacity, and the flux. There is W and P, which is the topological fugacity and the flux. So any fugacity comes with flux, right? This is fine with you?
Yes.
How do you see duality in TSU2? You swap them, right? But when you swap this relation, so you swap WP and FN. But this is not true unless you impose the condition that F1 plus F1 multiply F2 is 1 and N1 plus N2 is 0. If you don't do this, it's introduce a phase. Okay? And this phase is to cancel the phase that is compensate this. So what I'm saying is that this relation hold without imposing F1 times F2 equal to 1, N1 plus N2 equal to 1, okay? And this thing. And how do you see this is a mixed Chern-Simons? Okay, good. Tau is the topological, right? N is the flux for the flavor, right? You see this? This is tau to the N. So topological raised to the flux of flavor. F is the flavor and is raised to the flux of topological. Does it answer your question?
Yes.
Type of,
So I was just asking, like, can I just explicitly see this in the localization computation by adding a...
no, this you have to impose in the sense that, so it depends on how you define TU2, right? So this TSU2 coming from the Lagrangian description, U1 with 2 flavor. And then you say that there must be a mixed Chern-Simons that come from the couple, the two U1 symmetry together. And if you multiply it, you get this TU2 with this property. You can do that from the description, right? Okay. Now my point is that you can gauge these two symmetry together. So this is how it look like. Okay. So you multiply. There should be only one of them. Sorry, there should be no. This is the typo. Sorry. So combine this. There should be only one copy here. So what I'm doing here is the following. I take one copy of TU2 and I gauge both Higgs and Coulomb symmetry together. Forget about this part. This part is a typo. Okay. So there's Z1, C2, M1, M2, Z1 inverse, C2 inverse, minus M1 minus M2. Okay, and you integrate. And these are the result. And if you add one flavor, you can compute from the similar formula, you get this. So since this is the end of time, let me wrap up maybe. So let me interpret what does this mean, okay? So if you have superconformal index, what you can do is that you can expand in the fugacity X. This is the same fugacity as counting delta plus J3. For SCFT, delta is a conformal dimension plus this J3, okay? So if you expand, you can study the matching of the superconformal multiplet. This is taken from various paper here. This is 3D equal to 2 superconformal multiplet, and this is contribution to the index, and this is the contribution of various multiplet. Okay. Now, since we know that what is important here, let me emphasize there are some important role here that the blue guy plus X. So we don't have, suppose that we don't have free field in the theory. Forget about these two. Suppose we have only interacting SCFT. So plus X is an irrelevant operator. Plus X squared come from marginal, minus X squared come from conserved current. So there is a nice theorem that say that contribution X squared of the index come from marginal minus conserved current. Okay, this is really useful. However, we can even do further step because our theory has at least n equal to 3. So we can assume that all the multiplet in our theory of n equal to 3, and then you decompose into n equal to 2. So you can see that flavor current decompose into relevant operator, which I denote in blue, and the conserved current. And extra SUSY conserved current appear only here. And we only use the index up to X squared, okay? We're not gonna look at the further order. So the crucial observation for 3D n equal to 3 SCFT is that if you look at coefficient of X, this is n equal to 3 further flavor currents. Coefficient of X squared, this is n equal to 2 marginal operator minus flavor current and extra SUSY currents. And this extra SUSY current will tell us whether the supersymmetry get enhanced or not in the infrared, okay? So this is the power of the superconformal multiplet combined with the index. By the way, there is nice work here and a lot of nice work here, which we combine together. So let's just look at this theory, and this is the index. So let me explain to you why simply this theory, we can only see we can already see supersymmetry enhancement. So look at the index of this theory, expand index. 0x mean no n equal to 3 flavor symmetry current. So basically also mean that no gauge invariant operator with R charge 1, okay? Indeed, you can see that the Higgs and Coulomb branch of moment map of TU2 is traceless. So there's no operator of R charge 1, okay? Furthermore, there's no marginal operator also. So because of the property of this, the moment map again of the Higgs and Coulomb branch of TU2, which is basically U1B2 flavor. Okay. Now, if you look at minus x squared has to come from n equal to 3 flavor symmetry current plus n equal to 3 extra SUSY current, which is 1, right? Because the coefficient is in -1. So current introduced -1, okay. And we know that this piece is 0 because of the order x. So you conclude that there must be 1 n equal to 3 extra SUSY current. And then you conclude that SUSY get enhanced from n equal to 3 to n equal to 4, simply by this. So indeed, this symmetry, this k, when it's greater than or equal to 4, is flow to the infrared with n equal to 4 supersymmetry, even though the description has n equal to 3 supersymmetry. So this is the technique that we do. Okay, so now you can look at what about k equal to 3. So let me ask organizer, I need 5 more minutes, is that okay?
Yeah, that's fine.
Okay, so I'm gonna finish soon. So k equal to 3, there's some very nice thing happening. So again, 0x mean that the theory has no n equal to 3 flavor symmetry current. As if you look at the table, this is what you can conclude. Again, the same argument hold, no n equal to 2 marginal operator. Minus 2x squared, compare this thing. When you decrease Chern-Simons level from greater than 4 or say 4 to 3, you have this piece minus x squared become minus 2x squared. This is extremely interesting. Meaning that n equal to 3 flavor symmetry current plus n equal to 3 extra SUSY current must be 2. However, there is no flavor symmetry current, so you conclude that there is 2 n equal to 3 extra SUSY current. So you're tempted to conclude that SUSY get enhanced from n equal to 3 to n equal to 5, but this turned out to be wrong. The reason is that n equal to 5 stress tensor multiplet in 5 of SO5R decomposed into, if you decompose the multiplet carefully, you will have to have plus x, not 0x. It's contradict here. So you cannot have n equal to 5. So the only thing you can conclude is that this theory is a product of 2 n equal to 4 superconformal field theory. And therefore you have 2 copies of n equal to 3 extra SUSY currents. And indeed, for this k equal to 3 specifically was studied by Kang and Yamazaki, found that this is a product of 2 copies of some theory that enhance symmetry to n equal to 4 in the infrared. Okay. Now, let me tell you about this. This has real n equal to 5 supersymmetry. So indeed, there is a coefficient 1x. So you can conclude that there is 1 U1 n equal to 3 flavor current contribute plus x. But if you remember the table, the flavor current of n equal to 3 has to contribute two places. One is this place, and one is another place is here, okay, as a minus sign. And you see that there are 2 extra red terms here that indicate that there are 2 extra SUSY conserved current carrying topological charges plus 1 and minus 1. And SUSY get enhanced from n equal to 3 to n equal to 5, okay? N equal to 5 stress tensor multiplet decompose into n equal to 2 multiplet in consistent way. So you get 1x in consistent. It satisfies all the conditions we know about n equal to 5 supersymmetry. Now, if you view this as an n equal to 2 perspective, you see that this term indicates that the theory has, from n equal to 2 perspective, not n equal to 3 perspective, you would conclude that this is SO3 global symmetric current. Indeed, because there are 3 terms. Okay? This is indeed the commutant of asymmetry of SO2 inside SO5, which is SO3. So it's kind of consistent to our observation that this theory has n equal to 5 supersymmetry in the infrared. And with Gabi-Safria, we check that this particular theory doesn't match with any known n equal to 5 theory. So I tempted to say that this is a new n equal to 5 theory that arises in this way. Okay. So I can show you more example, but let me soon wrap up because I'm running out of time. This is you can also test duality. If you remember that there's duality that coming from moving the brane across the wall. Indeed, this is this duality. You can see that there are 2 duality frame. Manifest global symmetry are different. But of course, since they're dual, so one has to get enhanced, right? So, and indeed, you can compute index of the 2 theory, and you can match the index. This is usual story of duality, and you can see operator map in an interesting way that meson of one theory become meson dress monopole of the other theory. Okay, so and this is the story about S-duality, about gravity dual. So since I'm running out of time, so let me probably conclude. So what we have seen here is a new class of 3D SCFT from a local SL2Z action. We have seen supersymmetry enhancement. We have seen various interesting dualities. I hope interesting. And okay, you can generalize this in various directions. So you can generalize to 4D n equal to 1 theory, for example, motivated by duality wall in a 5D n equal to 1 gauge theory. Here we find global symmetry enhancement in a lot of theory in 4 dimensions with n equal to 1 supersymmetry. And this is n equal to 2 marginal operator. So yeah, so basically, and there is some open question whether this can be generalized to 3D n equal to 1, for example, or other theory, including, for example, T of G theory, which is other gauge group, which is self-dual under Langland's dual, for example. Okay, this is an open question. Okay, thank you very much for your attention.
Thanks, Noppadol, for that very nice talk. Maybe at this point we can unmute our mics and clap for Noppadol.
Thank you very much.
And if we can have more questions.
I had a question. So some of what you did looked very similar to what people call discrete gauging in maybe, I've seen the terminology maybe in 4D. Is this similar or is this something different?
I would say this is different in 4 dimension. Okay, so basically you used, this is not discrete, by the way, this is continuous. This is even non-abelian gauging. Discrete gauging, from my understanding, is like, for example, you could construct a 4D. Okay, it's similar in this sense. Okay, so discrete gauging, from my understanding, is that you take, this is how you construct a lot of 4D n equal to 3, not 3D, okay, 4D n equal to 3.
Mm-hmm.
So you take a subgroup, a discrete subgroup of some symmetry of 4D n equal to 4, right?
Right.
And say you go to n equal to 4 at the self-dual point, you take a discrete subgroup of that and you quotient.
Right.
You quotient in the sense that the theory preserve n equal to 3 supersymmetry in 4 dimensions. Okay, in that case, yes. Observe that you use the twisting in the sense that you use the gauging such that it's a part of the, you go to self-dual point, meaning you go to the point where S duality is a self-dual, basically, right? You go to self-dual point and you use discrete symmetry that belong to that point to quotient. In this setup, it's similar and different in the following sense. Similar in the sense that I take theory, which is self-dual, namely TUN, and I commonly gauge Higgs and Coulomb symmetry. Okay. I didn't take a discrete part of any S duality to quotient. So this is not discrete gauging. Okay. So I think this should answer your question. So no, I didn't take a subgroup of any self-dual point, but I used the self-duality. I used the building block which has self-duality, which is TUN. And then I commonly gauge Higgs and Coulomb symmetry. The result of gauging Higgs and Coulomb symmetry is that generically one should break R symmetry from SU3, from SU2 that act on Higgs and act on Coulomb separately. Now you commonly gauge them, so you should break these two diagonal. But the surprise is that in many of these theory, there is a supersymmetry enhancement, which from generically n equal to 3 up to n equal to 4, or in some cases n equal to 5. Okay, so in a sense, I wouldn't call this discrete gauging, but I would call this S-fold because it's the SL2Z duality twist on the theory which has S duality, self-S duality. But this self-duality is very different from 4D in the sense that this is the self-mirror theory.
Right, and there's no marginal parameter here in 3D.
A marginal parameter in which theory? I'm sorry. In these theories.
I'm saying one other difference is, unlike in 4D, in 3D n equal to 4, you don't have a marginal parameter.
Okay. This has to be clarified, this terminology. It's true that there is no n equal to 3 and n equal to 2 or 4 preserving marginal operator. This is
true. That's what I mean. Yeah.
This is true. There is, however, n equal to 2 preserving marginal operators.
Okay.
Like for the n equal to 4, you have, this is an analog of beta deform and this kind of thing that you preserve n equal to 1, n equal to 4, basically. But I agree with you that if you want n equal to 3 preserving, n equal to 2 preserving, there's no such thing in 3D.
Okay, thanks.
So I had a somewhat slightly tangential question regarding this theories, n equal to 5 theories that you obtained by enhancement.
Yes.
So you said it is not, it doesn't seem to be any of the known theories. I assume that you mean like this, and so on and so forth.
Exactly. This is a surprise in the sense that this is an ongoing work, by the way, with we collaborate with Gabi Safria. So since this is an ongoing work and it's not finalized yet, so I would say I can tell you what we have found so far is that usually n equal to 5 that we know so far is belong to ABJ class, right?
Yeah. Which are usually O into SP or something.
Yes, exactly. So we try to match the index and we could not find any. Of course, you can ask, but this is not the exhaust the possibility. I agree. I mean, yeah, n equal to 5 is still not much explored. No.
Yeah, so you could match the index, of course. But I was thinking whether there's something that you can do at the level of the branes, like
brane. I see.
Can you just lift it to M theory somehow? You know, do a T duality from T to B and then lift it to M theory or F theory or something, which kind of then you can identify it with M2 probing something.
Yes. So excellent question.
Yeah.
We don't know, first of all, we don't know M theory of this of this setup, even at large. Suppose that you take, instead of 2D3 brane, you take ND3 branes, let's say. A gravity dual for this model was not clear because you add matter. I don't know why. Usually, if you don't add matter, there is an M theory realization of this thing. This is due to, I should give credits actually. This is due to lots of nice work actually, due to Terashima Yamazaki and Dongmin Gang and various people that I should cite here, that pure J4 theory, you can realize on M5 brane on 3 manifold. It's a close cousin of this thing. But once you add matter, which is crucial for n equal to 5 here, by the way, we don't know the M theory. I asked a lot of experts on the 3 manifold. I mean, with matter, it's become unclear. What's the M theory construction? Mm-hmm. Of course, it would be nice to identify this in the future.
Mm-hmm. Okay. So one other question, which is probably even more tangential. So, like people like Bagger and so on and so forth have been saying that at least the various n equal to 5 and n equal to 6 theories that you obtained from M-branes probing various orbifolds and so on and so forth, they all have this 3 algebra structure. At least the older n equal to 5 theories which were studied. Like, is there a way of checking the 3 algebra structure for this n equal to 5 fixed point? Like, is there some way of checking that?
I have to say that yeah, no, I don't know answer along that line. That's a nice question, but with the 3 algebra, I don't know how to start this theory in that notation or in that language actually.
I guess is there a imprint of the 3 algebra structure on the index? Since you have the index, then you can, if the answer to that question is yes, you could imagine that.
Could compare. So you mean the index of BLG theory?
Yeah.
I think we look at it, but well, we look at the OSP class of theory. So far, probably we haven't found anything so far that match with this index.
Yeah.
So we scan. It's a scanning. I mean, of course, you can ask what about more complicated background that might preserve n equal to 5. This we cannot answer.
Okay. Okay. Thanks.
Thank you. How are you doing? We haven't seen each other for a long time.
Many years. Yeah.
Yes.
Fine. How are you? How are things?
Yes, I'm doing okay. Thank you.
Well, are there any more questions for Noppadol? If not, let's thank Noppadol again.
Well, thank you so much again to all of you, and hope everything is going fine there also.
Yeah, thanks a lot. Thanks for the talk.
It would be good if you could visit us, Noppadol, sometime. Yeah, whenever.
Yes, definitely. After this mess, I would like to be able to travel again. Thank you.